Welcome to Group 22's Critical Design Review presentation for the Arcane Game Board. Our group consists of 3 computer engineers, Lucas Lage, Fernando Valdez-Recio, Anton Strickland, and 1 electrical engineer, Kayla Fordenberger. What is the Arcane Game Board? The Arcane Game Board is a magical chessboard allowing 2 users to play the game without ever touching a single piece. To play, users will indicate their desired moves using a simple web application and the board will respond accordingly. Our group particularly enjoys tabletop games, and chess has been a staple board game for centuries. Our group felt compelled to add a unique and fun twist to it. The COVID-19 pandemic required people across the globe to stay inside and socially distance from one another to prevent the spread of disease. The Arcane Game Board idea came about as a way to implement long-distance gameplay with friends while still utilizing a physical board. We figured chess would be a great game to design for, since it is extremely well known and has seen a rise in popularity due to recent mainstream media. Overall, our group wanted to do something fun for our project that we could see ourselves using in our own households. Our major goal is to create a seamless gameplay experience, which we hope to achieve by ensuring accurate and timely piece movement. We don't want our pieces to move too slowly and disturb the flow of the game, and we also want to make sure our pieces avoid collision when in motion. In addition, to set our project apart from being a regular chessboard, we want to have the board able to operate without any human intervention once the board is set up. And finally, since this project has a wide variety of potential consumers, we want to make this project as user-friendly as possible, both within the web application user interface and the setup of the board. In order to accomplish our goals, we outlined several technical specifications which can be seen in the table on this slide. They include size and cost requirements, which directly affect the potential consumer. Additionally, we specify how quick and responsive we estimate the board should be as to not hinder the flow of chess games. I will now discuss our project design approach. First and foremost, we broke down each team member's role in the project as it relates to the major aspects of the project. The color of each block and the letter in the top left corresponds to the team lead. Subsequent letters correspond to secondary leads. Here we have our hardware block diagram. The color of each block corresponds to the status of each part: research, design, prototype, or complete. This block diagram depicts how the main components of our hardware connect and relate to one another in general. The main component from the hardware diagram that makes this whole project possible is the microcontroller. After careful consideration, we chose the ESP32 Room 32D because it seemed like a good middle ground between the options we were considering. One of the major benefits of the ESP32 is the integrated Wi-Fi and Bluetooth module, which vastly saves complexity in regards to our PCB design. Another significant component decision was our motor driver selection. We decided on the TMC2209 stepper motor driver by Trinamic. The sensorless homing, stealth chop mode, and large voltage range made it a particularly good candidate. There are 2 operation modes available. For our purposes, we will be using the mode which utilizes UART to pass information back to the MCU. Our ESP32 only supports 2 UART connections, which means the 2 motors will eliminate any additional UART connections to our microcontroller.
Hey, my name is Fernando Valdez-Recio, and I'll be going over the hardware design of our project. The movement of chess pieces is handled by a Core XY system that runs just under our playing surface. In a Core XY system, 2 stationary stepper motors are used in conjunction with 2 belt loops to move a central carriage along X and Y as shown in the diagram. Motion in the system is not straightforward, as each motor contributes to both X and Y movement. The equations of motion show that spinning a single motor results in a diagonal motion rather than a linear motion found in other Cartesian systems. We chose this system because it is extremely space efficient, and we would not have to worry about running motor wires to a moving motor. We decided to implement an H-bot variation of the Core XY system, as it uses less pulleys, relies on a single belt loop, and keeps pulleys on a single plane, unlike the original Core XY. The drawback of this variation is that motion along X creates a significant torque vector. This vector doesn't exist in the original Core XY, as the crossing belts in the original cancel the torque on this axis. We thought we could build a sturdy enough system that the additional torque on this axis wouldn't be an issue. This design is simpler, which cuts down on component costs and is even more space efficient than the original Core XY. This system also shares the same equations of motion as the original Core XY. Stepper motors have been widely used for applications where positional accuracy is crucial. For our design, we're using two NEMA 17 stepper motors. 3D printing has become very popular, and most printer models use these motors. This has led to their mass production, which brought very cheap costs. They have been widely used thanks to their ability to implement open-loop position control. This position control is what will allow us to move our chess pieces across our playing surface accurately. Our HBOT and game board were designed using SolidWorks. Each red component seen in this assembly was designed by yours truly and was printed on my 3D printer. This CAD model let us validate components when we were down selecting parts and gave us an understanding of how everything would fit together when assembled. Each of the moving carriages is actually a clamshell design with linear bearings sandwiched in the middle. Each half of the clamshell is held together using two M5 bolts and two embedded M5 nuts. Here we see an early assembled version of our HBOT CAD model. Unfortunately, I was all out of red filament for this print job. A plank of 3/4 inch pine was used as a base to keep our build sturdy yet lightweight, as it's not a very dense wood. Brass threaded inserts were drilled into the plank to accept bolts that hold down the HBOT. This allows us to repeatedly thread and unthread these bolts without wearing out threads in the wood. One of the biggest challenges faced thus far was overcoming the X-axis torque mentioned earlier. My original design had recesses in the clamshell carriages that the linear rods slid into. The tolerances in these recesses were too loose and caused a lot of wobble. I fixed this by heating some of the bushings, seen on the left, with a soldering iron and pressing them into the plastic recesses. These bushings hugged the linear rods much better and almost completely eliminated wobble. Another issue was the lack of metric hardware at local stores, especially the threaded M5 inserts that went into the wooden base. Luckily, Amazon had any small metric hardware I needed, like the threaded inserts seen on the right.
Hi, my name is Kayla Freudenberger, and I will now talk about the electrical design for the Arcane game board. As the sole electrical engineer, I am in charge of designing the power supply and the printed circuit board. To supply our PCB with power, we decided to use a 12-volt adapter wall plug commonly seen in many household devices to handle the AC to DC conversion. We have three components in our design that need different voltage inputs. Our ESP32 microcontroller needs a 3.3-volt input, our electromagnet needs a 5-volt input, and our TMC2209 motor drivers need a 12-volt input. Given these requirements, we need two DC to DC step-down voltage regulators, a 3.3 for our microcontroller, and a 5 for our electromagnet. For our 3.3 volt and our 5 volt voltage regulators, we ended up selecting the LM2596SX switching step-down voltage regulator manufactured by Texas Instruments. This particular regulator was not only in stock, but also operated comfortably within our parameters, as we can see from the table. Additionally, this voltage regulator requires few external components to operate, which was a huge plus in terms of our PCB design. For our PCB and schematic design, we decided to use Autodesk Fusion 360 because it allows you to create a team and collaborate on the design together, which proved extremely helpful. We are using JLC PCB to manufacture our board and do a majority of the surface mount assembly. We had been planning to use JLC from the beginning, so we intentionally sought out parts that were in stock. Unfortunately, we ended up running into a problem recently where the TMC2209 motor drivers we selected were out of stock. We considered many potential solutions, including redesigning to use the TMC2208s, however, these were also out of stock. Ultimately, we decided it would be best to redesign our original board such that we could slot in our TMC2209 dev kits. This problem ended up setting our timeline back for our PCB order, but we are currently waiting its arrival. This particular page of our PCB schematic design contains the two voltage regulator schematics and the power jack for the 12-volt AC-DC adapter. The input and output of both regulators are labeled, and these labels will be used to indicate connections across separate design sheets. During the design of these schematics, I realized that these voltage regulators required non-standard size power inductors. For the most part, we are using size 0805 for our basic components. However, power inductors are much larger because they have much higher inductance as a result of the DC to DC conversion. Our second sheet for our PCB schematic includes our ESP32 microcontroller and our relay, which will allow us to turn our electromagnet on and off as needed. The connections to our ESP32 are extremely important to get right because the ESP32 will be controlling all the moving parts of our project. As per the microcontroller's hardware design guidelines, we've added capacitors to the power supply to avoid potential power rail collapse. Additionally, we added an RC delay circuit to the EN pin to ensure power supply to the ESP32 during power-up. For our electromagnet, we decided to use a relay to toggle it on and off for moving the pieces across the board. As is typical when designing schematics with a mechanical relay, we've included a flyback diode in parallel with the inductance coil to prevent huge voltage spikes when the power supply is disconnected. This schematic is for the USB connection that we will be using to flash firmware to our ESP32 microcontroller. We've included 2 physical push buttons on our PCB for reset and pair. The connections are for an external USB breakout board that we will be using. It should be noted that the USB breakout board will not be a permanent attachment and will be removed once the firmware is flashed. This slide contains both version 1.0 and version 2.0 of the PCB schematic for the TMC2209 stepper motor drivers. Since we ran into problems with part availability for the TMC2209, we decided to redesign so we could slot in the dev kits we've been using. Prior to the redesign, this schematic was by far the most complex and took the most time to design. After generating the board, we needed to organize the components on the board in such a way that it would be most convenient to connect external parts like the motors and electromagnet. To make testing easier, I used boxes to outline and label the main circuits, such as the 5 and 3.3 volt regulator. This will make it much easier to identify any issues and fix the schematic if necessary. Aside from that, I followed datasheet recommendations for IC and external component placement. There have been several challenges specific to the PCB design that we've encountered so far, the first being part placement and size requirements for certain components. Another challenge has been getting accurate footprints for certain components. Finally, the biggest challenge has been component availability. As discussed earlier, we had to change our initial voltage regulators due to being out of stock, as well as the issue with our TMC2209s. The lack of component availability has set back our initial timeline for ordering our PCB. However, as mentioned earlier, we are expecting our PCB to arrive shortly so we can begin testing.
Hello, my name is James Anton Strickland. I'm the lead firmware designer for our project. First, we'll start with a firmware block diagram. You can see here that we have multiple classes interfacing with each other, but our primary class, the one used to drive overall function of the robot, is the robot controller. It handles initialization of the stepper motor drivers, as well as spinning up a game controller, which is used for each chess game that's played. Each chess game also includes a wireless receiver, which uses the integrated Wi-Fi module in our CPU to connect to the web app, which then sends JSON files to be parsed into strings and then converted into robotic movement. We're going to go over the structural overhaul that was required at the beginning of the semester, the introduction of the robot and game class, the challenges faced outside of the code, and some of the unit tests. Initially, we were going to use firmware called Marlin. This is a 3D printing firmware that is very widely used and open source, so we thought it'd be a good basis. Unfortunately, it's overly complex for our needs, and it also is built for a different task. This led to me using an object-oriented programming design that focuses on using classes and inheritance to save us time on development and to make the code more readable, if a bit less efficient, than Marlin. We've decided to implement a more robust game and robot state controller than was initially intended. For the robot controller, this takes the form of something akin to a slicer, or a piece of software that converts pure software or files into robot commands, as briefly mentioned in the earlier class diagram. For the game controller, this is something that was originally intended but is now more complex as it has simple movement commands but also handles transposition. What this does is make sure that when a piece is moving, if it were to collide with another piece, invalidating the physical and digital game board parity, instead shifts it over, so it travels on the border between tiles instead of in the center. We've also faced challenges in the libraries that we were initially intending to use. This takes the form of Espressif IDF versus Arduino framework, as well as library deprecation. The Espressif IDF, if you aren't familiar with it, is essentially an alternative to Arduino that's maintained by the actual manufacturer of our MCU. The problem is that it's not nearly as robust of a library as usually intended for more industrial applications that we weren't familiar with. This led to us using the Arduino framework, like originally intended, but having to refactor some of our libraries. We ran into issues here though, because many of them are designed for hardware that's either more robust or in some cases lacking in safety features that we have on our own device. Most commonly, this results in a watchdog timer error, forcing a reset, and then making it so all of our state is lost. Here you can see our unit test progress. We're still in active development, which you can see with the features that are listed in each category, but things are moving along quite quickly now that we've finalized our libraries and finished the refactor that we need to do at the beginning of the semester. Hopefully we'll be able to get some of our stretch goals in. I'm particularly looking forward to a Bluetooth feature that'll have users using a bespoke app rather than a terminal to log the board into their own Wi-Fi networks.
Hi everybody, my name is Lucas Lage and I am the lead software developer for both the web application as well as setting up the web connection between the web application and the microcontroller. Our software design consists of 3 separate steps: a front-end design, a back-end design, as well as a WebSocket connection between the web application and the microcontroller. For our software block diagram, our data stream is quite direct. We have a player which will provide input directly to our front end. That front end will provide a UI for our player, which is going to actively interact with both our back end, which is the MySQL database and Node.js API, as well as directly with the chessboard through a Socket.io WebSocket connection. A quick overview of what we're going to be covering for our software design is broken down into those 3 separate components as mentioned. We have the front-end design, where we use tools, frameworks such as Redux, and we're going to discuss our data flow, as well as our back-end design, where we discuss tools, API endpoints, as well as our design. And finally, we have our WebSocket connection, which we utilize to connect to the microcontroller using Socket.io. And we're going to talk about making that connection, as well as how it's going to work with the firmware. The front-end design consists of 3 main tools: the React framework, the Material UI CSS library, as well as the Redux data storage system. We use these 3 tools cohesively in order to provide a universal, multi-platform, progressive web application, which is capable of running on a wide array of computing devices, from very talented desktops all the way down to the older style of laptops. We also have expanding goals of providing a tablet as well as a mobile view, which the progressive web application would then support. In terms of data flow, we utilize Redux to hold data on the client side of the application. And so with having this data on the client side, we have it readily accessible, similar to that of like a global variable as you can imagine in other programs. Having these quote-unquote global variables makes data very easy to access. And we can easily make an API call somewhere in our application and have that data readily available wherever we need. An example of this would be that we would store some login information using Redux in order to provide that level of validation when it comes time for a user to sign in. Using Redux, we no longer have to make that additional API call, which would save bandwidth as well as make the application run smoother. This instant validation is one of the many tools that we're utilizing in order to provide a very quick, snappy, and functional application. For our backend design, we utilize 2 main tools, a MySQL database as well as a Node.js API. With the API designed as a REST API and our MySQL database a relational database, this makes for a very easy to use data center for our front end. We pair to our front end using the API endpoints that are provided with the REST API. And this allows for us to quickly update, add, and delete data rows as we see fit. We chose the relational database design because it works very well with the types of data sets that we will be storing. The final component in our web application is the WebSocket connection. And for this, we utilize Socket.io. We utilize Socket.io because of its easy-to-use nature in connecting a web application to external devices, such as that of a microcontroller. We chose the WebSocket connection for its bidirectional data stream, which would allow us to send information from the web application to the microcontroller, as well as return information from the microcontroller to the web application, without the need for polling or making any API calls. The instantaneous delivery of data makes it very easy to use in both our application as well as for developing the firmware that's actually hosted on the chessboard. As mentioned in previous slides, the chessboard will host a series of firmware which will then read the incoming chess moves coming from the web application and convert those into robot movements, where the robot can then read and detect which pieces need to be moved to which locations.
Now we will go over the administrative content. Here we can see our most up-to-date budget. Since this project is self-funded by the team members of this group, we are aiming to keep this as inexpensive as possible. Ideally, we would like to keep our budget below $500, which we are currently on track to achieve. However, this budget is not entirely finalized and is subject to change. Here, we included a breakdown of our estimated overall project progress, and we broke it down into 4 categories: research, design, prototype, and testing. We have completed essentially all the research we need for our current design and are primarily focused on designing and prototyping. Once our PCB arrives, we will be able to do much more testing of the project as a whole. Altogether, we are confident we will be more than able to complete this project by our deadline. Here, we have included a few bullet points detailing what our immediate plans are moving forward. This concludes our critical design review presentation for the Arcane game board. Thank you.